Hi, everybody. Welcome to this webinar on simulating a molecule on a quantum computer by one qubit. I'm Justin Lefebvre at Institut Quantique of University of Sherbrooke in Sherbrooke. We are very happy to have you with us today. This webinar is within a series of webinars that we prepared for you. We called that initiative Curieux Quantique or Quantum Curious. And if you're not yet subscribed to the Curieux Quantique, we will put in the chat right now the link you can use to subscribe to this initiative. We have both, we use both languages depending on your preferences within our communications. So you will receive the right stuff for you, depending on what language you want to use. Well, yeah, we're very happy of having this webinar that we prepared in collaboration with one qubit today. Without further waiting, I will introduce Dominic Marchand, Head of Research and Partnerships at one qubit, and Elizabeth Bennewitz. She's a researcher in the Hardware Innovation Lab at one qubit. Dominic and Elizabeth, welcome. It's great having you today with us, well, you can now unmute your mics and start talking about this exciting topic of simulating a molecule on a quantum computer.
Merci, Ghislain. Thanks, Ghislain. So I think I'll start because I just want to paint in broad strokes a little bit who one qubit is and what we do. And then I'll try to make that quick so that we leave as much time as possible for Elizabeth to tell you about the real topic today and simulating molecules. I'll just share my screen here in just a second. Just to be consistent so that the whole event is in English, but I feel free to ask questions in French if you want. Obviously, with my accents, I do speak some French. Happy to be answering questions in French or English later. So share screen, there we go. All right, let me just have a look at the time. So I'll keep you for about 10 minutes or so. After that, we can just need to move this away. There we go. So who one qubit is. This is something that is a little bit difficult to do in just 10 minutes. So I'll have to give you just the broad strokes, like I said. But one thing I wanted to say is I wanted to start with is us having opened our office in Sherbrooke here. There's a lot of things I want to forget about 2020, but our office opening is going to be one of the very, very positive things that stays in my mind from 2020. It's been an amazing experience. We've been here, we came here because of the talent and because of the amazing ecosystem that has been built for years here in Sherbrooke, and to be part of it. So it's been a very good start, and there's so many exciting things coming just around the corner starting 2021. So I can't wait to get started. Just in numbers, to start with who one qubit is, we were founded in 2012. So it's been roughly 7 years, close to 8 years of exciting progress. We are by now 130. So when I joined, we were only about 12. So that's on a factor 10 already. Quite a few patents, quite a few interesting papers, and now 3 offices, one in Waterloo and one in Vancouver, where our headquarters is. So how do we present one qubit usually? Whoops. This is the slide usually that if we want to do a very, very short presentation of what we do, that's what we use. So you have one qubit here in the middle and redefined intractable. So what does this mean? Essentially, it's pushing the limits, but it's pushing the limits by using advanced hardware. So either emergent hardware, so obviously quantum computing here is of interest today, but it's also a little bit broader when we look at the big one qubit family. We do all sorts of interesting and advanced hardware. And on one end, we try to build the bridge between those and the industry problem. So we're not that interested in a toy problem or just small proof of concept. Unless if they're like a stepping stone toward an actual industry problem or something that's relevant today. So building a bridge between what's coming and what's existing already and those industry problems has been our mission since our creation. Now, yes, if you look at 1-qubit as a big iceberg, like the visible part of it is quantum computing, quantum software. Although other parts are starting to be a little bit more noticed as well. So we've been very active in machine learning as well. So essentially, what we think is that if you want to go after a large goal of a revolution in solving problem in the industry, using hardware that's been developed on the medium to long term, you need to start building also on classical and existing state-of-the-art technology. And 1-qubit has been very effective at harnessing this expertise that we've been building to produce other interesting products. So I'll be mentioning a couple of those things also on the side, but just know that we do a little bit more than just quantum computing. So machine learning is one that's worth mentioning, because we do, for example, a lot in healthcare there. We do specialized hardware acceleration and hardware innovation. So Elizabeth, that we'll be presenting to you, is from that group. Many of the people we hired so far in Sherbrooke who are working for 1-qubit are also working in the hardware innovation lab. We have also, of course, quantum computing, quantum simulation, quantum chemistry. So some new people joining our team even today as we speak in the Sherbrooke team. So I'll be also quickly mentioning this a little bit later. So if you get back to that picture of the industry and the advanced hardware, on the industry side, we've been active in different industries, so different sectors. A few of them have been a little bit more of a focus. So advanced material, healthcare, and finance/insurance we've been very active there. But we did have a little bit of activity or a little bit of project in many of those other ones that you see here. So we're pretty broad. So you can say we're, yes, hardware agnostic, but we're also a little bit industry agnostic to some extent. Looking at the time here, so don't want to take too much of your time. So some of those slides will have more materials than I have time to present to you today. So maybe let's go on the big keywords here. Lots of commercial experience building solutions, not just in North America, but also Asia and Europe. Multi-year revenue engagements. So consulting work is something that we do, but we also develop partnerships and products. Strategic partnerships also with hardware partner providers is something that we're really well connected on the hardware side. Let's put it this way: major ones, but also smaller ones that have unique value proposition. So for a small company that's just under 130 employee or so, there's a few interesting things that I find are pretty unique. So a company of our size usually doesn't get invited to the World Economic Forum in Davos, but we've been there for a couple of years. Sole software partner of both Microsoft Azure, Quantum, and AWS Bracket at launch. We have developed some interesting products so far. X-ray is one that I suggest you go have a look, because that's very relevant today. It's the only class 3 medical device based on machine learning that's been approved in Canada. Other things related to cloud-based optimization. We also have some product with our collaborators, the Chicago Mercantile Exchange here in Chicago. Chemist, of course, here is going to be very relevant. So this is a suite of software tools for quantum chemistry. We won't be presenting Chemist today because it's an introductory talk, but if you want to learn more, please do reach out. Collaboration, so I already mentioned this, so let me continue quickly. And close ties to high caliber research institutions. So part of the reason why we're here, of course, Institut Quantique, University of Sherbrooke, but we're also well connected at the Quantum Intelligence Lab at the Perimeter Institute, for example. Most of our employees have started as or are coming from a research background. So we're really grounded in research and hope to stay really well connected with those institutions. So today is a great example of what we hope to be able to help later. So I'm going to skip most of those things and just read to you the titles because we don't have time. But yes, quantum simulation, that's the group that basically focus on quantum chemistry, and other quantum algorithm. Many interesting collaboration as well, including DAO. Hardware innovation at 1-qubit, I already mentioned. We work with different type of partner. From what we learned from the software side and digging deeper, we help them either improve or recommend specific problems for their hardware. So there's quite a bit of activity being done on this end as well. Machine learning, that's mostly on the healthcare and finance side. Can't say too much more today. And optimization, of course, it's another big area where we're pretty active. And just to finish, I wanted to maybe mention a couple of very interesting highlights. So one that was announced only a couple of weeks ago that's somewhat related to quantum chemistry, or that's very related to quantum chemistry. So there was a call for projects in quantum innovation by the Ministry of Economy and Innovation back in January, and we were lucky to get one of our project, a collaboration with us and on nanotech, get a 1.5 million project founded. So On Nanotech is a deep tech company based in Montreal that does something very interesting. They do water capture from the atmosphere. So in places where you don't have access to drinkable water, that type of technology is going to be revolutionary. So we have a partnership here to help them and work together to simulate the molecules that are of interest here for this process. X-ray, I mentioned a little bit earlier, very interesting machine learning work to detect anomalies in X-rays. We do, again, this is machine learning, but also quantum physics. We made the cover of this Nature Machine Intelligence journal in September. Very interesting paper if you haven't seen it. And we also have here on quantum machine learning. So it lets me touch on other topics that are of interest to us. And we're well over my 10 minutes, so I'm going to just say that we have different type of ways to work with people who want to get involved in quantum. Some of it is really just learning a little bit more about what the technology is promising and to see what's coming. So is your business going to be impacted? So it's a very light type of engagement, might mean some workshops, some tutorials, but we also have multi-year collaboration where we work together on projects to make sure that we do a very effective knowledge transfer to your team when you're building your own team. This is the type of engagement we have with Dow Chemicals, for example, a large company that's also very relevant to quantum chemistry today. I can't tell you a lot more about this given the time we have, but I really encourage you to reach out if you have questions, especially if you're in the Sherbrooke or Quebec region. Like my role is to make sure that we're connecting Qubit and the ecosystem here. So I'll be more than happy to make the connection or to connect you with the rest of the big Qubit family. I'm going to stop here and pass it on to Elizabeth, who's going to tell you about or introduce you to simulating molecules on quantum computers.
Thanks, Dominic. All right, well, thank you all for coming and good morning. I'm Elizabeth Bennewitz and I'm a researcher at Qubit's Hardware Innovation Lab. And today I'm going to be talking to you about simulating molecules using a quantum computer, which is one of the interesting applications for near-term quantum devices. So today I'll give you a brief outline of what I'll talk about. I'll start off by discussing the current state of quantum computers, and then go into simulating ground states and why this is something we're interested in doing on these near-term devices. Then I'll discuss how you actually go about representing states on a quantum computer, and then put it together to discuss finding the ground state energy using a variational quantum eigensolver. And I'll break for questions at the end, and then we'll go into a demo where I'll show you some code about how we actually build this variational quantum eigensolver and use it to find the ground state energy of the H2 molecule. So near-term quantum devices, or noisy intermediate scale quantum devices, or NISQ devices, are quantum computers of about 50 to 100 qubits, where that number 50 to 100 qubits is the size of our system, and it also indicates the types of problems that we can look to solve on these devices. And these NISQ devices promise to surpass the capabilities of classical computers when used to solve the right type of problem. And they can be applied for these quantum classical algorithms where you delegate the computationally difficult part of the computation to a quantum computer, and then you aid that quantum computation with some classical algorithms, which are very, very well studied and very stable. However, these NISQ devices are limited. So we have imperfect quantum control. So that means that we have imperfect control over the quantum computation itself. And they're also really limited by the effects of noise. So that quantum computation is very noisy and that reduces the accuracy of our output. And also they are relatively small. So 50 to 100 qubits might seem like a large number, but it's actually pretty small when we look to all of the different types of problems we hope to solve on quantum computers. The good news is that an application of NISQ devices are simulating ground states. And the reason we look at that is because simulating quantum chemistry sits at the intersection of the potential for quantum speedup from applying this problem to a quantum computer, as well as achieving practical applications both in research and in industry. And we can also pose these problems in a way that suits the hardware economy of current devices and the resources that we have access to right now. And we're interested in simulating these ground states of molecules because characterizing ground states are very important for encoding the system behavior at low temperatures, which tells us how a molecule, how a system behaves in its sort of most normal common state. It's also the first step to understanding the molecule or understanding the system at all. Before you go about trying to understand excited states or even how they react to other molecules, you first need to understand the ground state of your molecule. And this can also help us explain the electronic structure of atoms, which is something that we're going to go into today. And it can also be used for interesting chemistry, such as calculating reaction rates. The thing about these molecules is that ground states and these molecules are inherently quantum mechanical systems, which means that the states, so the way that we describe these systems, grows exponentially in system size. So we need to think about how we're encoding these states in a way that's efficient. So if we have a two particle system, then we have 4 quantum states that we need to describe, and that's relatively easy for us. We can do it on paper if we wanted. But if we want to expand that problem to 20 qubits, we now have 1 million states to take into consideration. And that becomes very, very hard, and that system becomes quickly intractable or unable to be solved classically. And also these quantum mechanical systems have inherently quantum mechanical characteristics, such as entanglement, that are really hard for a classical computer to represent. But the good news is even though this is classically hard, it's very natural to use a quantum computer to tackle such problems. Because quantum computers themselves are quantum mechanical systems, they're able to encode these quantum characteristics of our ground states very naturally. And also it can help us reduce the size of the system that we need to simulate because quantum computers can represent those states very, very well. But how do we do this? How are we going to find these ground states and find the ground state energy of these molecules? And the first thing to understand is that finding the ground states of quantum system or finding the ground states of any system is an optimization problem. And what that means is we have some sort of energy curve like the one on the left, and we want to find the point that is the lowest, that corresponds to the lowest energy. So that function that we want to optimize, so the function we want to minimize and find the minimum value of is our energy function, where we have some sort of trial wave function, which describes our quantum configuration. So the wave function is the mathematical object that basically encodes the information about the quantum state. And typically what we're going to do in order to solve an optimization problem is choose some sort of function to represent that wave function with variables that we can control. So we can control those variables to then find the lowest energy. And the way that we're going to find the energy for a given quantum configuration is using the Hamiltonian. So for those of you who aren't familiar, the Hamiltonian is the mathematical object that's going to encode all of the physics and all of the chemistry of our system. And it really tells our wave function, it tells our system how the molecules will want to behave, and it encodes all of that information. So as we're solving an optimization problem, what we're going to do is try to find the parameters or the optimal parameters, theta star, which correspond to the trial wave function with the lowest energy. So once we've found those optimal parameters, theta star, we then say that our ground state is approximately equal to that trial wave function evaluated at those optimal parameters. And then our ground state energy is approximately equal to the energy of that configuration, which we use the Hamiltonian to compute. Now, this trial wave function is what we're going to be using a quantum computer to represent. So as I discussed in the previous slide, those quantum mechanical states are what's really hard to do, encoding very quantum mechanical characteristics such as entanglement, but also that scaling. So we're going to use a quantum computer to represent this wave function and then find the optimal parameters which give us the lowest energy. So the first thing to understand about representing states on a quantum computer is to understand how quantum computers represent information. So classical computers represent information using a classical bit, which takes its value 0 or 1. But a quantum bit, or a qubit, represents information as a superposition of those two states. So it can be a 0, it can be a 1, but it also can be some sort of combination in between. So I like to think about this as a classical bit is like a light switch, it's either on or off, but a quantum bit is like a dimmer switch where it can be at any setting in between off or on. The one thing though is that quantum bits or qubits, you have to measure them to access. So we don't have direct access to that quantum mechanical object. We have to measure it. And when we measure it, it collapses to a classical bit. So if we have a qubit that represents some superposition of 0 or 1 and we measure it, we'll either get a 0 or a 1. But if we take repeated measurements, we'll get a set of measurements that are both 0s or 1s, depending on the probability distribution of that qubit. And when we want to look at doing some sort of quantum computation on these qubits, we are going to be building a quantum circuit. And what a quantum circuit is it takes some qubit on the left-hand side or some set of qubits, and it passes them through a quantum gate. And it basically takes this quantum state and it applies a quantum operator on it so that we have some transformed state on the right-hand side. And for the sake of our problem, we're going to be looking at two different types of quantum gates, which are 1 qubit rotation gates and 2 qubit entangling gates. So 1 qubit rotation gates take your single qubit state and it rotates it by some set of angles, theta, and then you have a rotated qubit on the right-hand side. But then a 2 qubit entangling gate is you have some set pair of qubits on the left-hand side and you entangle them. So you apply this inherently quantum mechanical operation to that state. And then you have on the right-hand side this a final wave function where the 2 qubits are entangled and they have a measurement of kind of a quantum mechanical interaction between them. So let's put this together to figure out how to represent a trial wave function on a quantum computer. So recall that we want to find a function to optimize this trial wave function. And the way that we're going to do that is by setting up a variational circuit. So on the left-hand side, we're going to have a bunch of qubits that are initialized according to some standard procedure. So in this case, it's just a bunch of 0 qubits. And then we pass them through a set of quantum gates. And in this case, it's going to be a set of these 1 qubit entangling gates and then these quantum entanglers. So recall that those 1 qubit rotation gates had the parameter theta. And that's what we're going to use as the control over our wave function. So at the end of the circuit, you've passed it through this variational circuit, you have a trial state, but we don't have access to this state. We don't have direct access to this state. And instead, we need to take a bunch of measurements on those qubits. And in particular, we're going to take projective measurements, which for your purposes right now, just think of projective measurements as very informed measurements based on the Hamiltonian of our system. So based on the system we want to simulate. And then we're going to take those projective measurements and we're going to use them to compute the energy. So putting this together into the variational quantum eigensolver, which is one of these quantum classical algorithms that we are interested in applying to NISQ devices, we're going to delegate that computationally difficult part of the task to preparing the quantum state on the quantum computer. We then take measurements on those states. Recall that measurements kind of collapse this quantum state onto a classical string of information. And then we take those measurements and we input them to a classical computer, where we use the classical computer to estimate the energy of our trial state based on those set of measurements, as well as the gradient. So the gradient is just the slope of that energy surface that I showed you before, and it tells us how to change the parameters in order to minimize the energy. We then use a classical optimizer to update the parameters of our trial wave function. So it's to update those rotation gates, and we pass it back to that quantum computer, and we repeat this step. So we repeat this process a bunch of times until we've found energy that is the lowest energy, where the next step we take, we aren't actually getting a lower energy. So this is called convergence. So we're trying to find or go through this algorithm until we've converged to the energy that is approximately going to be the ground state energy. So let's look at finding the H2 ground state energy with this variational quantum eigensolver. So the pseudocode for this algorithm will look like this. So when I go into the demo, I'll structure the code to be very similar to this. We'll start off by constructing the H2 qubit Hamiltonian, which again encodes all of the information about our system into the problem. We then choose to prepare a trial state, which in our case, we're going to be looking at a hardware efficient quantum state. And I'll go into a little bit more depth about how this quantum circuit is in fact hardware efficient. We're then going to choose the number of projective measurements we want to take on our circuit, as well as choosing the classical optimizer. So once we've set up our problem, we are then going to optimize it. So during the optimization, we're going to be preparing the quantum circuit with that set of parameters. We take those projective measurements, estimate the energy, and estimate the energy gradient. So again, that slope, which tells us how to update the parameters of our system in order to reduce the energy. And then we'll see what our outcome is and see what our estimated ground state energy is. And all of these purple lines are the ones that we're doing on a quantum computer. And for the sake of this particular simulation, I will be using a simulation of a quantum computer. So it's not actually using real quantum hardware, but we can create for very small systems, very accurate numerical simulations using classical devices to understand how these quantum computers will behave. So before I go to the tutorial, are there any questions about what I just covered?
So Elizabeth, there's 2 questions right now on the Q&A if you open it.
Okay. I don't know if I can with the open presentation.
Maybe I can read it to you.
Yeah, that sounds good.
So thanks for your question. So it says, when we say that the quantum computer makes the measurement of the qubit Hamiltonian, what's exactly going on underneath? Projective measurements on pure states or POVMS? So let's see. I might be a little bit, yeah, on pure states or mixed states. Yeah, go ahead. So there's a second question after.
Okay. Yeah. So when you have a perfect quantum computer, you're taking measurements on a pure state. But if you have a noisy quantum computer where those quantum controls are imperfect, they introduce a level of mixed. It mixes the state, so it's no longer completely pure. And then what you're going to do with the Hamiltonian is you get certain Hamiltonians. So you'll write your Hamiltonian as a sum of Pauli terms. And then those Pauli terms tell us which projective measurements we want to take. So we will, if we have a set of XXX on 3 qubits, we're going to rotate our trial state at the end into the X coordinate system and then take measurements on those qubits.
So the follow-up, like the rest of the question says, for NISQs, I think the usual initial states we start with are ground states, so state 0, or HF state, depending on the problem at hand. What about passing in random mixed state density matrices?
Yeah, so one of the reasons we start with the same state, so for example, the all 0 state, or the HF, which is the Hartree-Fock state, which is sort of a quantum, it's a quantum chemistry tool that we can find out before we know the real ground state, which gives us sort of the most dominant contribution of our ground state. The benefits of starting with all 0 or Hartree-Fock state is for all 0, you're starting your trial state always with the same initial point. So when we pass through those through the variational circuit, we're getting, minus effects of noise, we're getting approximately the same state. So if you start with random matrices or random sets of qubits in the beginning, when you pass the parameters through your trial state, you're going to end up with a different state. And so that becomes harder to optimize. I'm not sure if there's a way to do this while like keeping this in mind during your optimization, but that is two of the reasons why we're interested in starting with a standard state so that we prepare the same trial state or approximately the same trial state each time. And then a lot of times people start with the Hartree-Fock state because it can give you an informed starting space, starting state for your computation. And it's usually beneficial in all computational physics to use as much theory as you know about the problem to improve your computational analysis of a particular problem.
Another question, so would a NISQ be able to handle it, or is it possible to get reasonable results only in the future after NISQ era?
Yeah, so this is a good question, and I'll discuss it a little bit more in my tutorial where I'll show you an example of the noise model of a current quantum device. The problem right now is that even for small systems such as H2 or lithium hydride, there's still a lot of noise in the quantum computation. So for those systems which are pretty easy to solve classically, we're seeing kind of significant errors. But so that's why we're looking at NISQ devices to try to solve larger problems. So when we can scale these problems to larger molecules, which we don't have answers to classically, or are very hard to solve classically. And then one tag-along point is that even though the quantum calculations are pretty noisy, there's a lot of work that's being done to try to mitigate errors. So it's this field called error mitigation, where you take the output or the noisy output of a quantum computer and you hope to improve it using classical post-processing or additional methods to try to salvage as much as you can from that quantum computation. So in the NISQ devices, it'll probably be some combination of quantum computers with noise, but also error mitigation techniques that allow us to push through and achieve and solve problems that we weren't able to solve classically.
So I'm taking them in order of them being posted. The next one was on the chat. Do you simulate the superposition property of quantums? I think that might be related to using a simulator for the tutorial.
Sorry, could you say that again?
It says, do you simulate the superposition property of a quantum system, I'm assuming, or quantum?
Yes. So you can simulate it for small systems, but when you get to larger systems, it becomes very difficult.
Right. And another one that was posted right after, what kind of QC, so quantum computer do you work on? Ion traps, superconductors? So I guess the answer here is pretty much many of them. So we do have partnerships with IonQ, for example, who do ion traps. They had some very interesting results posted recently. And we do work with superconducting qubit companies as well. And then the second question is, how is your implementation different, better with respect to other VQE such as Penny Lane or Qiskit?
So I will be using Qiskit's VQE algorithm. For the sake of this tutorial, it really helps show there's a lot that goes into constructing these variational quantum algorithms. So I'm using some of these pre-done programs to show you guys the capabilities for something that's already been very well developed. And
if the question is intended to ask, what about our chemist software tools? A big selling point of those tools are the problem decomposition techniques that are being developed in Tune so that we can harness NISQ device, but also classical simulators as well. But that would be a better question for somebody on the chemist team. So if you want to learn more on this, I invite you to reach out. Next question is, if the number of particles, electrons, is conserved, can we choose an ansat in such a way that we can search in a smaller space?
Yes, actually, that's a really important point. So when you have the number of particles conserved and when you have the parity conserved, which are very common things in a system, so you can actually reduce your problem from something, let's say, from 4 qubits to 2 qubits, depending on some of these transformations you make. So when you represent your Hamiltonian, when you transform your Hamiltonian from electronic structure theory to second quantization, and then finally to the qubit representation, you can make a really key decision right there to represent it in a way that allows you to reduce the number of qubits that you need to simulate the system. And this is something that researchers do a lot because we currently are working on devices that are limited in the number of qubits, but also are very noisy. So if we can reduce a problem from 4 qubits to 2 qubits, or from 12 qubits to 10 qubits, that's really something that we want to do to make available or take advantage of or deal with the resources that are available with current quantum hardware.
Cool. So next question by an anonymous attendee. The weakness of the variational principle is there's no way to know if the trial function will produce a good estimate of the ground state. How restricted are you in your choice of trial functions?
Currently, so I'll be discussing the hardware efficient variational ansatz, which is this variational ansatz that was introduced to be tailored specifically to the capabilities of superconducting hardware. So we have limited number of gates that we can do and operate on the quantum chip itself. So we are constrained to using a trial function that's built with gates, or these quantum gates that can be implemented on our chip and on our quantum hardware. So that does limit our expressibility of our trial state. But the idea of putting these problems and solving the variational principle on a quantum computer, or using that to represent the trial state, is that these variational circuits are much more expressive than some classical counterparts, or are much more general, like the general trial state is more expressive than something that you could have on a classical computer.
So how much more time can we take for questions? Is that we have 1, 2, 3 more at least?
I think we should transition to the demo.
So maybe we can get back to the questions that are still here after the demo, if there's still time left. There's some interesting ones coming too. So.
Okay, yeah, that sounds good. Okay, I'm gonna switch. All right. So let's go into this demo, and we'll be using Qiskit to study and simulate these problems. And in particular, I'll discuss constructing that H2 qubit Hamiltonian, and then this trial state and what that variational circuit looks like. I'll set up the variational quantum eigensolver and then use it to find the ground state energy for H2 using 2 different noise models. So this I'll just skip. These are just packages that we import, and then this is for logging information that I'll just produces the plots that I'm about to show you. So the first thing that we want to do when constructing the H2 Hamiltonian is specify a bond separation that we're interested in simulating. So when you have 2 hydrogen molecules, we want to say, well, how far apart are they? And so we specify some given bond length, and then we use that information as well as this qubit mapping. So like that one question where I asked if we could reduce the number of qubits, this transformation right here, where we use it to transform our Hamiltonian from our previous representation, which cannot be represented on a quantum computer, to a function that can be represented on a quantum computer, or sorry, can interact with a trial state representation on a quantum computer. And in particular, we choose a Jordan-Wigner transformation, which will then tell us what our qubit Hamiltonian will look like, the number of qubits that we need to simulate this Hamiltonian in this state, as well as the energy shift, which is the constant energy in our system, the number of spin orbitals, and then the number of particles. So right here, we're going to generate the qubit Hamiltonian. And when we generate that qubit Hamiltonian, it'll tell us how many particles we're going to be simulating, as well as the number of spin orbitals. So we use this PyCF driver, which is a quantum chemistry tool, and it just accesses all of the information that we need about the H2 molecule. And then we use a set of transformations to convert it into a fermionic operator, and then finally to a qubit operator. So let's look at what the output of that is. So the number of electrons in our system is 2, which means that we have 2 electrons in our simulation. And then we have a number of 4 spin orbitals. And for those of you who are familiar with spin orbitals and molecular structure, we have 4 different orbitals that have different spins. So for the first hydrogen, we have a 1s orbital with a spin up location, and then we have the same 1s but spin down. And then the second Hamiltonian has that same set of 1s spin up and 1s spin down. So then we're going to be modeling where those electrons are occupying which spin orbitals. And the number of qubits that we need for this simulation is 4, and that's with this particular Jordan-Wigner transformation. If we wanted to, we could reduce it using a different transformation to a problem with 2 qubits. But for the sake of this tutorial, we're just looking at the 4 in the standard transformation. So because this system is very small, we can actually solve it classically. We just convert the Hamiltonian to a matrix, and we just solve it using exact diagonalization to find the eigenvalues and eigenvectors. And when we do that, our ground state energy of our system total is negative 1.13 Hartree. And that's split up into 2 different parts. One is the computed part. So one is the part of the energy that we need to find the specific ground state for. And then the other part is this constant energy contribution from the Hamiltonian. To give you guys a look at this Hamiltonian in qubit representation, it's a sum of Pauli operators, which are like the identity operator X, Y, and Z. And so these are the terms that we're actually going to use to put in our projective measurements. If we have a measurement, or we have a term in the Hamiltonian that has X, X, Y, we're going to make a measurement that gives us information about the state's value when we measure the state. So when we look to construct our trial wave function, we're going to be constructing a hardware efficient variational circuit, which was defined in this IBM paper here, where we are building a circuit based on the number of qubits needed to simulate the molecule, as well as the number of layers, which tells us how many rounds of these rotation gates and entangling unitaries we need. And the reason that it's hardware efficient is because we only have a certain set of gates that can be operated or can be done on a superconducting qubit, because Qiskit is IBM's tool, and they build superconducting qubits. So they have rotation gates that are native to their device, as well as CNOT entangling gates. So those are the 2 building blocks of our variational circuit. And then the next thing that we need to do is define some sort of qubit connectivity, which tells us which pairs of qubits can be entangled together. So we don't, on superconducting qubits, we don't have unlimited entanglement capabilities. So we can't entangle every qubit with every pair. We're limited to a certain set. So we're going to construct this circuit by first building a quantum circuit right here. This tells us that the object that we're building is a quantum circuit. And then we apply an initial rotation gate to every qubit. And then we'll construct an entanglement layer based on the number of pairs that we have. And then we'll finish it with another rotation layer. And so at the end of the day, what does this look like? If we define some qubit connectivity, like I mentioned before, because we're limited with the number of qubits that we can entangle, and we say, okay, well, what if it's just linear? So the 0th qubit can only be entangled with the first qubit, the first with the second with the third. And so if we print this circuit, it looks like we have 4 qubits going into our simulation. We have a set of rotation gates right here with the parameters. These P00s, their P number, are the parameters that we are going to change in our optimization problem. And then these blue gates here are our entangling C0 gates. So they'll operate very specifically on their pair of qubits and entangle them. And then we finish it up with another rotation gate. So let's put this together. So our variational quantum simulation, I've made a function right here, which takes as an input our molecule. So it's that H2 Hamiltonian molecule that we've created, which has all the information about the number of qubits we're interested in solving, the qubit Hamiltonian. And then the other important part is we're going to input a quantum instance, which is Qiskit's way of consolidating all of the information about the quantum computer simulation that we want to solve. So it tells us how many measurements we want to make on the variational circuit. It says, oh, well, is there a noise model? Are we modeling quantum noise in our simulation? And also it encodes information about that qubit connectivity. So that hardware efficient element where we can only entangle certain pairs of qubits. So I've also passed in a logger so that I'm able to show you guys what's going on during the optimization. So we are going to take that trial state that I showed you up above, and this will be our problem. We're only going to be looking at one layer. So like I showed you in the one before, we only have one round of these entangling gates. And we're going to be choosing the SPSA classical optimizer, which is beneficial to quantum computing because one of the resources we need to be aware of when doing a quantum calculation is the number of times we call our quantum circuit, because that is every time we generate a quantum circuit, that costs us time and also money, and it's also very expensive. So we just want to limit the number of times we actually have to call this quantum computer to generate the circuit. And so SPSA, for every optimization iteration, it only calls that circuit or calls the energy optimization, or sorry, energy evaluation twice. And then we want to do 200 angle updates to really show you guys how this trial function converges to a particular energy. So we use Qiskit's VQE algorithm and functionality, which inputs as an operator our qubit Hamiltonian, which will tell it how to make projective measurements. We then put in the optimizer as well as the circuit and that quantum instance, which again tells us how we're going to be controlling or specifying that quantum computation. And then we'll get our results. So we run it and we get a certain VQE eigenvalue, because again, what the ground state is it's an eigenvalue of your Hamiltonian, and that will be our output. So the first thing that I'm going to look at for the quantum instance, so the first simulation I'll discuss is the simulating shot noise, which is basically just a really fancy way of saying we are only taking a finite number of measurements on that trial state. So recall that image where I had projective measurements that you take on the trial state, which are used to calculate your energy. Well, because we have limited quantum resources, we have a limited number of measurements that we can make on that state. In an ideal world, you would make an infinite number of measurements and you get a very, very, very accurate representation of the estimation of the energy for that trial state. But the reality is that we're limited with the number of measurements that we can make. So we want to show you how through this computation, if we make 1,000 shots, so 1,000 measurements on our trial state for each type of projective measurement, how we're able to, what the optimization looks like. And then I'll also compare this shot noise simulation, which is also important to understand that every other part of this quantum computation is perfect. We're assuming it's ideal and it has no other noise. But that's not the reality of current quantum hardware. Current quantum hardware has tons of different sources of noise. It could be this imperfect quantum control where each gate has certain amount of noise or inaccuracies in applying its operation. It also could be some sources of depolarizing noise. But for what you need to know is that this, I'll be showing you the results of a VQE simulated on a noise model taken from a real device. So the first thing we want to do is this shot noise, so only looking at this finite sampling. And when we optimize our problem, this is what our optimization curve looks like. So on the x-axis, we have the number of optimization steps that we're asking our classical optimizer to do. And then on the on the y-axis, we have the mean energy of our simulation. So right to the left of that gray dash line, we just have some calibration steps, which basically allow us to make the best first step when we actually start our angle updates. And then to the right of that, we actually see our optimization itself, where it's going down. Sometimes it doesn't get quite as down, and then it keeps going, and then it gets pretty flat, where this black dark line is the exact solution found using classical methods, or specifically found using exact diagonalization of your Hamiltonian matrix. But over time, we see that it does converge and it gets pretty close to that ground state energy, but it's not exact. And part of that reason is because we have some noise. We have this measurement noise or shot noise that is keeping us from maybe getting the most accurate estimation of the final energy. However, this again is like with everything else ideal. So all of the other gates are operating exactly as they should. And so this is kind of showing the upper end of the capabilities of our quantum computation. But if we want to actually look at the capabilities of current quantum hardware, we want to use one of these mock devices, which are kind of convenient. So Qiskit allows you to have access and to simulate these mock or fake devices, which is really cool to be able to compare or simulate expected noise and expected accuracies out from quantum computations. So we can take a look at this hardware where by plotting this error map, where this center image with the numbers, sorry about the color, but those are the configuration of our quantum device. So this tells us which qubit pairs can be entangled with which. So we don't have a linear connectivity. We would have to choose 0 and 1, 1 and 2, 1 and 3, or 3 and 4. So we also have a particular type of entangling error. So this color shows us how accurately we can entangle those two qubits. And then also this readout error tells us how accurate we can measure those qubits. So if we do the same simulation for finding the ground state energy, so optimizing that energy function, but with a noisy simulator, this is the result that we get. So it takes a little bit longer, and that's because it's harder for our classical computer to simulate this quantum noise. It takes a lot more capabilities and it just takes longer. And again, we have this calibration step and then we drop down. But if you notice, we're actually a lot higher than the exact ground state energy, but we've still converged. And that's because this noise that's inherent to this device is keeping us from getting a really good estimation of our trial state. But we get fairly close, like we get something that isn't, it's by no means accurate enough to use it for calculations for quantum chemistry, but we're showing that we're able to navigate through this information space and find a ground state. And let's just compare these two simulations to show you guys. So the blue line is that mock device, that mock 5 qubit device. And then the orange line is the shot noise. So we see that they both were able to optimize around the same amount of time, although it's not always that comparable. And then they've converged to different values. And that's inherently because noise is a real limiting factor in current quantum computations, and especially for current devices. And as we look to near-term devices of these 50 to 100 qubits, the ability to mitigate through noise and the ability to take a noisy solution and still use it is a huge topic of research and a huge topic of discussion. So in addition to finding the ground state energy for a particular bond length, one thing that people do in quantum chemistry is to generate potential energy curves for a particular molecule. And then you find the lowest energy or find the bond length that corresponds to the lowest energy. And that will tell you the equilibrium separation between the two molecules. So we can do the same thing. And again, I've run this beforehand just because it takes a bit of time to do. It took us about 14 minutes to run both the shot noise simulation for 10 bond lengths, as well as the mock device simulation for 10 bond lengths. And this is our result. So we're comparing it to the exact diagonalization result, which is that classical solution. So that's the black curve, and we want to get our quantum calculations fitted down to the black curve as best as possible. And so the blue dots are our shot noise simulations, and then the red dots are the mock device or the fake Vigo machine. And we see that in all of these bond lengths, our shot noise device gave us a better estimation of our potential energy curve. And then for the fake Vigo, we had a certain amount of noise, which gave us an energy error between the ground state. And so as I mentioned, like one of current research field is how to mitigate the errors on these quantum devices and take that noisy output of the quantum computer found using that mock device or found using some real type of quantum device, and say, okay, well, this is a pretty good output. How do we improve it? How do we take the advantages that we were able to gain from a quantum computer, a quantum computation, and still salvage it to get useful information and useful problems to our answers? So this is the end of the demo part, and I'm happy to discuss any questions that you had from the previous conversation or about the code itself.
There's a few questions already, some left over, two left over from before. Can you see them now, or do you want me to read them as before?
I think I have to, wait, let me. No, I can't see them. Would you mind reading?
Yeah, no, I'll try to read. Although I'm not a great reader, public reader, I'll do my best. So starting with the questions from just before, I think there was two that were before. I'll just take them in order. So also when we use a parametrized circuit, we get access to only a polynomial Hilbert space, even though the actual Hilbert space is exponentially large. We are restricting the Hilbert space. We have to sweep through with the parameter variation motivated by quantum chemistry, etc. What if the energy landscape is too complicated and we end up missing the ground state we are looking for?
Yeah, this is a good question, because this is a question that we ask almost every optimization problem that we have. And one way researchers can tell us whether or not the energy surface is too complicated or whether our trial state isn't expressive enough is to study what's called the loss landscape of that energy function. So you have that energy surface curve, but if you don't know the answers to those functions, you don't actually know what that curve looks like. So there have been a lot of people who are trying to break into this study of trying to understand the loss landscape or this energy surface and how complicated and how many local minima there are, or how many saddle points there are, by understanding, by like characterizing those, they can characterize the number of kind of like maxima or minima in the surface, but it's very, very difficult to do that. So and then once they find some sort of characterization of that landscape, that will help people know how hard it is to actually optimize these quantum circuits. But it's a very much a ongoing area of research.
Quantum computing looks to work quite well for fundamental state. What about excited states?
Yeah, so there are ways people are trying to, so you can change your trial state to represent, you can basically tailor your trial state to be one that is better for representing your excited states. You can do something similar with variational principle, like this minimization of a certain function. So you could, excited states are also eigenstates of your Hamiltonian. So that means that the variation of, if you've reached the eigenstate, the variation of that eigenstate, or sorry, that trial state near an eigenstate is approximately 0. So you could do something where you're trying to find the minimization of, you're trying to minimize a function that would be 0 for an excited state. But that is a question and a lot of research that people are going into, trying to understand how you can best simulate excited states on quantum computers.
All right, next question. Is it just because of noise that the solution does not converge to the exact solution, or because of the limitation in the representativeness of the trial wave function?
Yeah, it's both. So whenever you approximate a wave function with some ansatz, or like some trial function, you're going to be limiting the space that you can explore. And so you're hoping that that trial function will give you an estimation that allows you to make a very, very accurate estimation of that state. So there's always going to be some limitation, but in current quantum computation, the limit is both the noise, but also how large of a circuit you can be, how large of a circuit you can construct. So you can improve that trial wave function if you add more layers. So you add more of these entangling operations, and that can improve the expressibility of your state. But with current quantum hardware, it's hard to build really large depth quantum circuits. It becomes too noisy, such that like the errors accumulate and your accuracy of your state becomes almost like equivalent to a random state. So we're limited by the depth of our circuit, and that also means that we're limited by the expressibility of our circuit. So as we go forward, people are really trying to focus on improving the accuracy and improving these noise models so that you can increase the depth and therefore the expressibility of your trial state.
Next question. While the ground state energy is not accurate because of noise, what about the state vector, which can be extracted from the VQE circuit?
Yeah, so actually, this is a really good point that we, as I mentioned, that trial state, we don't have access to it. So when I do a numerical simulation, so when I do a classical simulation of a quantum computer, I have access to it because we are asking our classical computer to keep track of that quantum state using classical methods. So I have access to it. But if I were to do this on a real quantum device, I do not have access to that wave function. So while VQE allows us, and representing this trial state allows us to represent a approximate wave function, we don't have direct access to it to be able to extract it. So you could take different types of measurements on that state in order to learn more about the wave function itself, but you need to be able, you need to think about interacting with that ground state using measurements in order to really learn anything, and to think about how we can use quantum computers to learn about the ground states.
This one's coming from the chat. Thanks for posting in the questions. Are there other quantum or quantum-inspired algorithms that could be applied to this type of problem? If so, what results have been achieved?
Yeah, there are. Specifically for VQE, you could, so a variational quantum eigensolver is a way to pose this optimization problem. So it's a way of minimizing a given function, and that function you need to represent using qubits. So if you can use in this VQE algorithm to solve a ton of different optimization problems, as long as you can pose your function or pose your question onto something that's like a qubit Hamiltonian. And then in addition, there are a lot of other kind of quantum classical algorithms that people are looking to solve on quantum computers. So there's like QAOA problems, which are similar to VQE problems that people are seeing interesting results for. I think a lot of solutions or outcomes of research or a lot of research right now is trying to prove and understand the noise and behavior of these algorithms so that when we get to the NISQ era where we have 50 to 100 qubit devices, we can apply these algorithms to problems that we can't already solve classically. Right now, a lot of the research is trying to kind of reproduce results that you can solve classically, but with these quantum classical algorithms.
All right, so here for the diatomic case, we are simply varying the bond length with a Born-Oppenheimer approximation. So how do we deal with for example, triatomic molecule like water, dealing with polar bonds and the influence of H bonds? What should we vary to find the ideal configuration of the molecule?
Yeah,
sorry, there's a second part to this. Maybe I should read the whole thing. These examples are under Born-Oppenheimer approximation and well-separated potential energy surfaces. How do we deal with the example, for example, Yan-Teller systems?
Yeah, so all of that chemistry that you're talking about, it'll go into constructing the qubit Hamiltonian. So up at the top here, where I construct the H2 molecule and I use this function to construct the qubit operator, this driver is kind of hiding all of the chemistry and all of the physics that goes into understanding the molecule. So it's kind of like, as long as you can pose those questions or how you can encode that information into a qubit Hamiltonian, you can then try to solve that problem on a quantum computer. Although that's completely an area of expertise, like it's an area of research of how do you construct Hamiltonians for different types of molecules, including the other one. I'm also not trained as a quantum chemist, so I'm not as familiar with that last system right there, but that's the answer to my question, is that a lot of these, answer your question, is a lot of the chemistry that goes into it, it's done before you apply it, and it's in this realm of research of how do you, answering the question of how do you pose interesting questions onto quantum computers.
Right. So I think it'd be interesting to pose those questions to our chemist team. But in general, I think you have to be able to write an Hamiltonian for it and then convert it to a qubit Hamiltonian. So hopefully the question you had in mind or the problem you had in mind is something you can write simply into a Hamiltonian, and something that that would take so many qubits that it doesn't fit on NISQ computers yet. Next question, Eve. Sorry, I haven't told anybody who was asking question directly. So hi, Eve. I hope you're doing well. Classically, there must be methods already existing for finding energies of excited states. What are these methods? I'm a neophyte in quantum chemistry, so neither of us are quantum chemists either. So, but Elizabeth, maybe we can give some.
Yeah, I don't have any off the top of my head, but I know that there are a lot of algorithms for finding excited states. I think a quick Google search of quantum chemistry algorithms for finding excited states will get you some interesting answers.
But I'm happy to connect you with some of our quantum simulation team who works in quantum chemistry, Eve, if you want to know a little bit more. I vaguely remember some paper on the topic, but it's been long since I looked at them. So I'll move on to the next question. With error mitigation techniques, would you be able to fall back on the shot noise model, or there are errors that we are not able to mitigate?
Yeah, so there are error mitigation. What's cool about the field of error mitigation is there's a wide range of different ways you can approach it. The idea would be to reduce noise or kind of post-process a lot of the noise that you encounter. So you could develop error mitigation techniques that target a specific type of noise on a quantum computer. So you could use it to target shot noise. You could use it to target like depolarizing noise. You could aim to improve or develop error mitigation techniques that can improve the output of a gate. So there's, I mean, ideally you would get to one of these noise-free models where you're only maybe simulating shot noise, but it can be very difficult to do that. And, or you could also create an algorithm that doesn't just look like, it could be specifically trying to mitigate noise on a given a specific noise model of a superconducting qubit device or an ion trap device, or you can develop error mitigation techniques that aim to improve a specific problem. So there's a bunch of different ways that you can do it, but the idea is to get to a very, if you're trying to mitigate noise, you're trying to apply error mitigation techniques to mitigating specific noise models, you're trying to get to this ideal circuit.
So there was, I'm not exactly sure what the question here is. I think it's a statement, but I think there's an underlying question on the chat here. We cannot see how the calculations are so good at or around the equilibrium state of H2 with VQE calculation. So I guess, are you asking why is it so good? Maybe that person can comment or give a little bit more details on what they're trying to ask. But
I think, well, I'll try to answer what I think they're asking, which is that like we know that so from the classical calculation, we know that the ground state will be, or the equilibrium value will be somewhere around here. But with our VQE, we chose, like, we have some noise. One thing that you can do is you can do something like this 10 different bond lengths, and then you can find, oh, well, the ground state looks like the lowest of all of those runs was this 0.6 run. Well, let's now do 10 runs around 0.6. And then you can keep doing that until you get more and more accuracy to find maybe a bond, like the bond length separation that's exact. So you aren't simulating maybe like every 0.01 from here till 4. So you can find a way to more reduce the number of simulations you need. But then we're also hoping that, you know, quantum computation, so even with this fake device, we know that the equilibrium configuration was somewhere around this bond length. Both the shot noise simulation as well as the fake Vigo simulation gave us the lowest energy around this 0.6. And the real equilibrium value, I think, is 0.7. So we would just do that with a smaller bond length separation and continue to find the lowest energy.
Well, I think there's some comments related to, I think you can all go see it in the chat, related to the answer to Eve's question. Do we have any other questions before we complete this session? I think we're getting closer to the end right now. So we have here one last question. Very, very interesting presentation. I'm curious. Thanks, Elizabeth. It was great. I'm curious in learning what type of molecule simulation Qubit is currently pursuing.
You're welcome for the presentation. And I think that's the best question asked to the quantum chemistry simulation team, because they're working on really state-of-the-art simulations, whereas my work is specifically trying to kind of make it work on error mitigation. So I'm looking at simpler systems, but they are the ones that are actually doing some of these really cutting-edge simulations of quantum chemistry.
Yeah, so I think that what we wanted this to be a little bit more introductory level, but we're hoping to convince the quantum simulation team to come and maybe do something more advanced in the next year, maybe in partnership with Curie Quantique. and IQ. So if there's interest there, then it's good to know, and we can maybe try to organize something. Otherwise, you can maybe have a look at publication that have 1QBit names attached to some interesting paper that have been published in collaboration with DAO. But there's going to be more coming in the next year as well. So I think that's a way of getting a little bit at that answer indirectly. Mm-hmm. Ghislain, should I read the next one that's just been posted there, or do we need to adjourn now?
No problem. Go ahead with the next question.
Quantum chemistry codes give the energy of the ground state at equilibrium distance with an accuracy of about 0.05 wave numbers. What is the accuracy of this Qubit calculation? So I myself not super familiar with measuring accuracy in wave numbers, but
yeah, me either. So I mean, I can answer how we can kind of understand the accuracy of these solutions. So there's that energy error, and even though we don't have direct access to that quantum state that's prepared on the trial function, when we are simulating something with a classical simulator, because we have access to it, we can use it to find what's called the fidelity of a particular state. So the fidelity tells us this quantum overlap or kind of quantum similarity between two different quantum states. So we can use that density, we can use like the density matrix of our quantum circuit to compute an estimation of the fidelity of the state. And that will tell us kind of how much overlap there is between the state simulated on the quantum VQE algorithm compared to the ground state. And for kind of smaller molecules, you get a very high fidelity. For larger molecules, the fidelity does decrease. And that's because there is going to be some inaccuracy with our calculation.
So there's, thanks for adding some details about what wave numbers are. I think that maybe we can take that conversation offline, sorry, to go further, but that was helpful. Any other questions before we close this webinar? Oh, maybe I should mention that there was a question a little bit earlier about whether the recording will be shared, and I think somebody from Institut Quantique answered. I think that the Jupyter notebook, so that's a question for you, Elizabeth. Do you think we'll be able to share that notebook as well with the participants?
Yeah, I think I can. I might need to change a couple of things, but yeah.
Great. So I guess that same as for the link to the video, I guess that if you want to have this Jupyter notebook, you can maybe write to us, and we'll make sure that we send the Jupyter notebook as well as the video link to the people that asked for it. Okay, great. Well, thanks a lot to you too. That was very, very interesting. I mean, and I see with the number of questions that we had that people in the audience also found it very, very exciting. And thanks so much for your detailed explanations, how it works. And I guess that this is just the beginning, as Dominic said. There is so much ahead of us, so many exciting research projects that are coming in. So, well, stay tuned for the next webinars that we will organize with 1QBit, but also next webinars of Curieux Quantique more in general. Maybe as a glimpse for the next two ones, the next one is on January 20th. With one prof here at Institut Quantique, Michel Pierrot-Ladrière, as well as Nizar Messaoudi from Keysight. They will be discussing about spin-based qubits. And the one after that, the one webinar after that is on February 17th with Martin Laforêt from ISERA. And they will help you understand the differences between classic and quantum cryptography, and why you should start thinking about post-quantum crypto today. So that's it for today. Thanks a lot for having attended this webinar, and well, stay tuned. And don't forget, you can always subscribe to Curieux Quantique if it's not already done. Thanks a lot.
Thank you, everyone. Have a nice day.
Merci. Au revoir. Thanks.